Hey, how's everybody doing? Hope you're having a good evening. I just was scrambling here to check my microphone. It looked like the levels were running kind of low. So I was let me know if this sounds too quiet, and if so, I'll do something about that. And I went and grabbed a water here, so I'm kind of in a rush. I went through a lot of the Mississippi products from Tuesday night to look at that situation and look at some of the severe forecasting parameters. And we'll go over a little bit of that here. Let me take a look at the chat. Yeah, somebody said it's a little bit quiet. Let me bring that up. Okay, that should be a little bit better here. Okay. All right, if you have any problems with audio at this point, just let me know, and I'm going to press right on. Okay. I think we'll go ahead and start and go back to Tuesday night, and this is the SPC outlook, or the SPC summary of all the precipitation reports. So we had an initial grouping about 3 o'clock in the afternoon in Mississippi, and then a lot of that spread up into Alabama later in the evening. So I finally got the radar data for that day. Bring that up real quick. And this is the initial storms that we started out with in the Jackson area. Run a loop of this. You can see they start out pretty isolated here, and then as we go on from about 2112 to 2130Z, start seeing these cells start to deepen a little bit and mature and develop a good rotation. And first ones is up here in Lexington County. Then one of the ones around in this area developed one of the initial tornadoes. So let me go back and see which one that is. 32, 44, 89, 76. That's going to be right down in this area right here. Going to be right there. So at about 2157, which is right around this time, tornado was being reported on this storm. So what are some of the indicators we have on this storm? Well, we do have the strong reflectivity gradient on the south side. So this is suggesting that we've got a pretty strong storm, but we should look at the velocity. And we have to be aware of where the radar location is, where the RDA is. So we're sampling the storm kind of like that. So let me switch over to base reflectivity. I'm going to shrink the window down so you can get a look at what I'm doing here. So this is uncorrected base reflectivity. And so it's showing very strong outbound here, but very weak inbound. So what might be happening here? There's so much red. What's happening is that the strong northeast motion of the storm is being overwhelmingly picked up by the radar. So we can subtract that out, and the GR level X products have these motion vectors. I'm going to set that to about 230 at maybe 25, and then we go to storm relative velocity. Now we can see these couplet signatures starting to emerge in that data. And let's see, what kind of couplet do we have here? Well, we have to consider where the radar is. So it's off to the southwest. So we're detecting inbound. Yeah, we're detecting outbound velocities right there, the red shades, and then we've got this green inbound. So this is showing that we have some pretty strong convergence in this area, and convergence is actually one of the early signatures that tends to precede PVS development. I tend to see that a lot. You can see kind of like a wall of convergence come together. And there's a slight bit of cyclonic rotation, because if you look at this core right here, it's slightly offset from the outbound here. So this is kind of painting some rotation developing here. But this is actually a very get an idea of the diameter on this couplet. We're talking about 2 miles. So at this point, it's showing mostly as mid-level rotation. I'm going to increase the velocity a little bit. See if we can bring out that couplet. The data looks very noisy here, and sometimes you can fix that to a certain extent by going up to higher tilts, and sometimes that cleans up the data a little bit. But we are seeing rotational convergence in this area. And we also have to be aware of the magnitude. So if we look at the bottom, we get this display. Actually, I'm circling the wrong thing. Right here, we've got this display of velocity where the cursor is. So I'm going to set that on the max outbound. We have 33 outbound. And then on the other side, we have 41 inbound. So that's about 70 knots of shear across the couplet. That's pretty good circulation within that storm there. See, as that progresses, I'm not going to focus on this storm too much because there's a lot to cover here, and I want to move on to the Alabama storm. See, 2200Z, we can see the circulation has strengthened quite a bit. We've got 50 inbound here and a very strong 44 outbound there. So that's almost 100 knots there of rotation. And the storm at this point is looking like that. And look at that, we've got a bit of a hook echo developing here. And sometimes on the spectrum width, we can kind of see the debris cloud. And it doesn't stand out too much here, but that might be what it is right there. Further back, you can see what looks like probably area differentiating the updraft right here with from the downdraft here with more uniform particle sizes there. Correspond there to the tail cloud to a certain extent. Or it could be a shelf cloud. I don't know. But the main part of the hook down here, let's see where the strongest rotation is. It's going to be down in this area. I'm going to set the cursor there, and that corresponds to about where we had that damage report, which was right there. Yeah, pretty classic hook echo there. Now let me load up the storm that occurred later during the evening in northern Alabama. So while I wait for those to load, I'm going to pull up the chat real quick and hello to our usual visitors here, Michael and Lexi, Ron, good to see you all again, and Sue. See Mark, Michael. This is the Huntsville radar, and we're going to take a look at the storm that spawned most of the fatalities here. Those were in the, I'm trying to remember the town, I think it was Rosalie. Anyway, Jackson County, Alabama, right there. There were 6 fatalities and looks like 7 to 9 injuries. And I'm going to go over the radar really quickly so we can look at the surface data and some of the model forecast parameters here. Now the overall situation, let me show that to you. Had this big squall line right here, and these were a few cells that were ahead of the squall line here in northern Alabama. And let me pull out the location of that damage, and Howdy's 3470 by 8576. Reading the display, bottom of the window to get that. So this is the storm that's heading towards our damage location. We roll this forward. Let me go down to 0.5. See, we've got a pretty good storm there. And this looks definitely more severe. You can kind of see the inflow area. And I'll show you this right here. Let me back up a little bit. So just before the storm arrived at that damage area, in fact, there probably was damage before that. But in any case, I'm going to go up to higher tilts here. You're going to see kind of what looks like a little weak echo region right there. So this is going to be up at about 5,000 feet. We go up higher and you can see what's basically a bounded weak echo region right in there. This is up at about 8,000 feet. And then at that point we've got overhang. Let me put the cursor here, in the middle of that core, and go down 14,000 of the surface, and you can see that's overhanging this area. So we're getting the updraft developing and rising very quickly in that area and forming precip and hail, grapple and all that stuff right over that area. So that's showing we have a pretty strong updraft right there in progress. And if I run a cross section, I show you a little bit of that right here. Yeah. It's a little bit shallow. It's only topping out at about 20 to 25,000. But let's see. That looks like that overhang area right there. Overhang, and then the weak echo region. It's going to be this area right here. Then this, so basically to recap, this whole area is the overhang, and then weak echo region here. The updraft winds. The inflow is coming in like that, and then rising up into the cloud here. So hopefully that makes sense. And let's see how let's see where all the rotation factors in. Now we got to keep in mind the radar is off this way now. So what we're seeing here is outbound velocity here and inbound. So we've got to couple it right here. This is probably our meso. We're detecting this up at about 8,000. I'm going to put the cursor right in the center right there. Compare that to the reflectivity. So it's kind of buried right in this area right here. And I can see it looks like probably some new circulation down here. So that may correspond to rotation in the updraft, in the main updraft area right there. Anyway, the storm heads on off to the northeast, and then we get that damage. Pretty classic there, 50 inbound and then 40 outbound. That's about 90 knots of rotation across a diameter about 2 miles. Don't see what looks like, don't exactly see a TVS in here. That's probably going to be a very shallow signature. Radar's mostly detecting the mesocyclone rotation here. Let me look over on chat and see if anybody has any questions about that. Michael says, on GR level 3, what would you say is the usual mid-level rotation area? Show that on the program. That would involve mostly just going up to the higher tilts. You've got a variety of tilts here. You would go up to basically what corresponds to 5, 10, 15,000 feet. That'll get you in the mid-levels of the storm, and you look at the storm relative velocity, and you check for rotation that looks like that. And basically, you kind of like stack that vertically, see what kind of rotation you're looking at each different level. A lot of times you'll have a TVS very close to the ground at the lowest levels, and then that stacks upward into the mid-levels into a large mesocyclone. So anyway, I want to keep this moving along. Stuff like this is probably good for a workshop. I'm going to show you a couple of charts here looking at the model data to show you why this severe weather happened. This is a forecast sounding from the 4-kilometer NAM, 6-hour forecast. That doesn't look very severe right there. Normally we see a very strong lapse rate. This diagram would be tilting more to the left in a severe weather situation. And what do our capes look like? Yeah, we got cape values in the 3 to 1,000 range, and 1,500 would be about the upper limit. So that's certainly on the low end. But helicities, those are up in the 400 range, so those are certainly supportive of tornadoes there. And look at the hodograph. This is a plot of winds with height, starting with the surface plot. And then I like this pivotal weather plot because it actually gives you the height in kilometers on each plot, and that's really critical data, and a lot of sites tend to miss that. So right here, I don't know if you can see that, but there's a 1 for 1 kilometer, 2 kilometer, 3 kilometer, 4 kilometer, and 5. So this is showing that winds at the surface, which is here, coming out of the southeast at about 15 knots. Winds at 1 kilometer, those are coming out of the south-southwest at about 50 knots. So that's given us a long shear line on the hodograph, and the curvature is what's really important. Because when we plot storm motion on this, see they plotted storm motion coming out of 230 at 45. What we look at is the area swept out between that and the ground, then a higher layer, usually 1 kilometer is selected, and the larger area you get in there, the higher the storm relative helicity. This is pretty significant here, definitely up in the tornado range. So what would help generate this? Well, incredibly enough, slowing down the low-level winds would help a lot in backing the low-level winds. What if we had surface winds at easterly at 20? Scratch that out. Okay, here's our new plot coming out of east at 20 at the surface. Our new line would look like that. So now look at all the area that would be swept out in here. So slower surface winds and backing are very important, and that kind of stuff is why we look for small-scale mesolows developing in the low-level field. That can give you a lot of that critical boosting of storm relative helicity. Okay, let's see here. What else should we look at? Here's those strong 850 millibar level winds. Those are kind of setting the stage across Alabama. You can see they're south-southwest at about 60 to 65 knots. That's pretty strong low-level jet in place there. So that combined with slightly southerly, weak low-level flow, that's going to give you very strong storm relative helicity. So here's what the radar looked like. The models actually missed out on a lot of this development in northeast Alabama. And I'll show you the 4-kilometer NAM forecast. Yeah, this is a 12-hour forecast for 6Z, the time of that tornado right there. Got the line correct back here, but it missed out on the development out ahead of it. So these models are not always going to catch the small details. And even 6 hours out, they were missing the development. The 6-hour forecast, this is the NAM 4-kilometer. Tornadoes right there at this time. Mesoscale model did not pick that up. So you have to kind of constantly be watching the weather and looking for these departures from actual model forecast data and what's actually happening out there. And let me show you one other thing before we move on. This is the significant tornado parameter down here. And the significant tornado parameter we had, that favored weak tornadoes. That was kind of in that range. We might want to do a special presentation on instability indices. That would be a good thing to cover. I'll show you the significant tornado parameter here real quick. This is the equation. I don't know how many of you are familiar with this, but this is basically a multiplicative equation. You can see there's 5 parts, and if you basically multiply the 5 parts together, any one of them are really high, that's going to bump the whole thing up. And the 5 things that we're looking for in this equation is CAPE, mixed layer CAPEs, and anything over 1500 is significant. We look for storm relative helicity, that's pretty important. Anything over 150 is significant. We look for bulk shear from the surface up to the mid-levels. 20 meters per second or 35 knots is pretty significant. The 4th thing that we look for is the LCL. The lower that is, the more likely you're going to have strong tornadoes. If you have dry air and dew points way down in the 40s and 50s, that's not going to give you big wedges or anything like that. And then the other thing is convective inhibition. The more we have of that, the more you're going to be able to support development at the time of max heating. If you have very weak convective inhibition, you're going to get a whole lot of cell competition. You're going to end up with lines and messy clusters of severe weather or of thunderstorms. I'll show you one other thing here. This is one of the severe weather indices from the 60s. This is the sweat index. Second here. And this is just kind of fun to look at to see what forecasters thought was important. Do we see any shear in this equation? Not really. We know that shear is very critical for severe weather, but this equation is only really looking at 850 to 500 millibar wind direction. It's not looking at the lower levels that are really important. And it's focusing very heavily on lapse rates and low level moisture. So it's taken a pretty different approach here. Anyway, what I wanted to kind of tell you about that, when I was talking about significant tornado parameter, they've got this thing here at Pivotal Weather that shows you why your levels are elevated. See right here, it's showing us that the LCL is factoring in to be pretty significant. So there's a lot of moisture. Also, storm relative helicity is kind of high, and the bulk shears are high. And then the CAPE is not really contributing anything. And, you can kind of look at that to kind of see what's going on. And you don't want to get too dependent on all these indexes. And that's why a lot of times I'll just kind of eyeball everything and, try to see what's happening. The other problem is the data tends to be kind of noisy, the numerical model data. Let me show you an example here. Now this is the storm relative helicity field. This is a 6-hour forecast. And you can see how even here there's noise in the data. You pull up a sounding for here where it's orange, you might get something really different from something that's here in the purple. All these wave things going on here. And the more complicated you make your instability indices, the more you're going to integrate these noise problems and resolution problems into your forecast equation. Another example, you see there's kind of a very mottled appearance here. This is the HI. So as we're dealing with these very small scale models, it becomes even more of a factor. The fields tend to be noisier and noisier. So that's why I like to kind of stay connected with the original raw data, focus on those. Okay, let's look at the surface chart for the, let me just look at the surface chart for that afternoon. Let you see this real quick. This is the setup we had. You can see we had south flow coming in off Louisiana. We draw isodrosotherms. The 70 line would look kind of like this. We'd have the 65 line. Probably something like that. And if we draw a 68 line, and this is basically showing we have kind of a broad moisture axis in place right there. And it's hard to find any strong surface boundaries. Sure, there are some in place here. There was, I think, a squall line earlier in the day. So we would have to be looking for outflow, that kind of thing, to be moving eastward during the day. Only when we go out further west that we find very clear boundaries at the surface here. Like that right there, for example. All right, so that's all I'm going to cover for now. We've done, good grief, that went on 25 minutes. So anyway, I appreciate you sticking with me, and I think we should do workshops for that kind of thing, maybe the next severe weather event we get. I'll kind of separate that out, and we'll do a separate program for that. So let's go into our forecast. Let's look at today. Like you saw in that opening reel, things were pretty clear outside. We had high pressure here in Texas and low pressure out in the Great Lakes. That's what's going on there. And a front moving into the eastern U.S., going out of the picture right there. But we do have thickness. See that thickness gradient in the southwestern U.S.? We'll have to watch for upper air systems to pick that up and start focusing frontogenesis on the west coast. That will be coming up here soon. In fact, you can see things already starting to tighten up here as we get anticyclogenesis out in the high deserts of Oregon. Cyclogenesis here, we've been watching that for a while. On Friday, that's going to take hold. We're going to start seeing showers developing Friday night. Abilene to San Antonio to Corpus Christi. The warm front's going to be well to the south like that. And we're going to see the system kind of scoot eastward over the weekend. There it goes, and it moves out of the picture, but not before developing a lot of isentropic lift, especially on the backside there. Here comes our next system on Monday. Coming in from the Pacific. See a lot of snow shower activity over Idaho and Oregon there. Going to move quickly to the east. By the time we do our webcast on Monday evening, going to be looking at a pattern kind of like this. Things are getting active out there in the Central Rockies and the Great Basin area here. You can see the thickness gradients are coming together very tightly in this. That's going to move eastward, and we're going to start pulling some polar air down from Canada. Draw the fronts on, so this is what we're looking at for Wednesday. I could swear, I think that the models might have come a little bit further north with this system than it did yesterday. So anyway, yeah, there's freezing precipitation starting to appear in northern Oklahoma there. And man, look at that 540 line coming in all the way down into Tyler, almost all the way down to Austin and down to Abilene. So we're going to have a very cold day coming up for Wednesday and Thursday. Things starting to get very active out in the northwest. Look at those strong gradients coming together here. Things stay pretty quiet in Texas, but we are building a new high pressure area. There comes our next outbreak. This is going to be Monday on the 12th, starting to get way out here. And this is where we're watching for an Arctic outbreak to come southward, and there it is. This is Thursday the 15th. Looks like the GFS has kind of backed away, kind of delayed this a couple days, and that's probably the cold bias emerging once again, but the models have been pretty clearly signaling a very strong outbreak for the 15th through the 20th, and I've seen that on the CFS model too. I really wish we had the ECMWF going out that far, but we don't have any access to that data. Very unfortunate. So get things queued up here, and I'm going to look at the chat before I sign off and see if you have... Where do I get the models? I use Pivotal Weather, and I appreciate them letting us use these products. That's going to be at pivotalweather.com. And does GR Level 3 have different levels for all the different products? Yeah, it does. I believe it lets you select all the different elevations, just like GR Level 2, so you should be able to do that. I'll probably go through GR Level 3 on the next webcast. Anyway, I appreciate y'all watching, and I hope you'll join us tomorrow at 8 o'clock. And I will be in San Antonio, and our webcast may be a little bit different, so check us out then. Have a good evening.